Hello, my name is Jared, and today I am going to be talking about an experiment performed by Sherwood and Gilligand in 1934. And so what Gilligand and Sherwood were exploring in 1934 was the mass transfer between the inner surface of a tube to a flowing fluid. And so what they used was a wetted wall tower. And what a wetted wall tower is just a tube where the inner surface of the tube is coated with a thin film of liquid, and then you have a flowing fluid through the tube, through the inner core of the tube. And in this case, they used air. And when they did their experiment, they ran this for 9 different liquids. And so they performed their experiment, got all their data, and then ultimately came up with this relationship, that the Sherwood number is equal to 0.023 multiplied by the Reynolds number to the 0.83 power multiplied by the Schmidt number to the 0.44 power. And this relationship is valid over the range of Reynolds number between 2,000 and 35,000 and a Schmidt number between 0.6 and 2.5. And so you might be asking yourself, what is this Sherwood number, Reynolds number, and Schmidt number? And what they are is just dimensionless variables. And by dimensionless, I mean they have no units. So we can talk about what each dimensionless variable is. So the Sherwood number is just the mass transfer coefficient multiplied by some characteristic length. In this case, it's the diameter of their circular tube they were using, divided by the diffusivity between the liquid and the air. That is just the ratio of convective mass transfer to diffusive mass transfer. And then the Reynolds number is just the ratio of inertial forces for the moving fluid over the viscous forces for the moving fluid. In that case, it's just the density of the fluid multiplied by the velocity of it multiplied by the same characteristic length as in the Sherwood. In that case, it's just the diameter of the tube divided by the viscosity of the fluid. And then the Schmidt number is just the ratio of momentum transfer to diffusive mass transfer. And that's just the velocity of the fluid multiplied by the diameter of the tube over the diffusivity for air and the liquid. And you might be asking yourself, where do these even come from? Well, when you're performing experiments, the first thing you have to do is consider the situation and what are the variables involved. And so for this experiment, what do you think the rate of evaporation will depend on? Well, it would depend on characteristics of the flowing fluid, the air. So that's the density. You also have the velocity of the moving fluid and also the viscosity. What else does it depend on? Well, you could also say it depends on the geometry. In that case, it's the characteristic length, so the diameter of the tube. That is going to be important to our situation. And then, since we're talking about mass transfer, we're going to have the diffusivity between the liquid and the gas. And then we also have the mass transfer coefficient, which is what they were after. And so if you're going to perform an experiment like this, you could explore this entire parameter space here, but that'd be pretty difficult. You see you have 6 parameters here, so if you're trying to find the mass transfer coefficient as a function of 5 parameters, that's going to be difficult. You could keep maybe 4 of the independent variables constant and vary the 5th one, and just go through and do that for every single one, but that's going to take a lot of time, a lot of effort, and also a lot of money. So what you want to do is you want to create a group of dimensionless variables. And what that does is it takes your entire situation and makes it only depend on these dimensionless variables. And the number of dimensionless variables you have is less than the variables that you started with, which makes the analysis much more simpler. And so first step is just to look at the units for every single one of our parameters. So put kilograms, meters, and second. And so density, what is that? That's just kilograms, so that's 1 per cubic meter, so -3 meters to the -3. And then there's no seconds. Velocity is just meters per second. Viscosity is just kilograms per meter second. Diameter, that's just meters. Diffusivity is meters squared per second. And the mass transfer coefficient has units of meters per second. And so what we have here is this is called the dimensional matrix for our problem. And there's a theorem called the Buckingham pi theorem that says the number of dimensionless groups that you need to describe a situation is equal to the number of variables minus the rank of the dimensional matrix. And what the rank of this dimensional matrix is just the dimensions of the column space of this matrix. So if you think of all the columns here and you take linear combinations of them, what number of column vectors do you need to be able to reach any point in that column space? And we're not going to be doing this by hand, but we're going to be using Python. I'll do that in a little bit. But we'll see that the rank of this is just equal to 3. And if the rank of this is equal to 3 and we have 6 parameters, then the number of dimensionless groups is equal to 6 minus 3. That's 3. And so we're going to call these dimensionless groups, so we're just going to call them pi 1, pi 2, and pi 3. Pi 1, pi 2, pi 3. And what these dimensionless variables are is it's a group of core variables that show up in each dimensionless variable, and then one non-core variable. And you just got to make sure that your core variables contain all the units possible. So kilograms, meters, and seconds for this problem. And then your non-core variables are just going to be the ones that aren't in the core variables. And you want to make sure that whatever you're after, in this case the mass transfer coefficient, you want to make that a non-core variable. So I'm going to choose for my core variables, I'm just going to put the density, do the diffusivity, and then we'll use the diameter of the tube. And that shows up in every dimensionless variable. And each of these is then raised to some power. So we'll put A, B, and C. And then for this second dimensionless variable, it doesn't have to be the same exponents as in the first one. So we'll just denote it as D, E, and F, showing that they can be different. And then G, H, and I. And then each of these dimensionless variables also need a non-core variable. So which ones haven't we used? We haven't used the mass transfer coefficient. We haven't used the velocity. And then we haven't used the viscosity. And these non-core variables, they aren't raised to any power. And your goal is to find the exponents A, B, C, in the case for pi 1, such that all the units cancel out and it's dimensionless. So let's just first talk about pi 1. the first dimensionless variable. We already see that that's the density raised to some power A, diffusivity raised to some power B, the diameter of the tube raised to some power C, multiplied by mass transfer coefficient. And so we're just going to plug in the units. So for the density, that's kilograms per cubic meter. It's raised to the A power. Diffusivity is just meters squared per second. That's raised to B. Diameter, that's just meters. It's raised to C. And then mass transfer coefficient, that's just meters per second. If we just expand that out, then we get kilograms to the A power. Meters, we have, from here we have negative 3A plus 2B plus C. Just remember that exponents, when you multiply, they just add together. So meters, we get negative 3A plus 2B plus C. And then we also have 1 meter here. So that's plus 1, a constant. And then we also have the seconds, which is negative B and then minus 1. And I'm going to be using Python to solve all these exponents for all our dimensionless variables. I'm going to show you how I'm going to be doing that. So if we just rewrite this, well, first of all, we know that the exponents all have to be equal to 0. So let's write down, we're going to get a linear system of equations. So A must be equal to 0 minus 3A plus 2B plus C. I'm going to take the 1 to the other side, so that's equal to negative 1. And then minus B is equal to 1, just like that. And now I'm going to rewrite this in a matrix form. So we got 1 minus 3, 0. We got 0, 2, negative 1 for the B column. The C column is no C in this one. There's 1 C here. And then 0. That's our matrix. Then A, B, and C is equal to the right-hand side, which is 0, negative 1, 1. And now you see that these columns here, this is the column for, these are the units for density, which is up here. The second column is just the units for diffusivity, 0 to negative 1. And then this column here is just the units for diameter, 0, 1, 0. And then that's what I could just call like a core matrix. I don't know if there's an actual term for it. I just call it the core matrix. And then over here, what is this? Well, it's our non-core variable, k sub c, 0, 1, negative 1. But it's negative times the column for kc here. So it's just negative 1 multiplied by the unit column for mass transfer coefficient, which is 0, 1, negative 1. And if you do this for pi 2, you're going to get the core matrix again multiplied by D, E, and F vector. And then on the right-hand side, you're just going to get the inverse units of the non-core variable. So with that, I will go over to Python, and I'm going to just solve all of these linear systems because I don't want to do it on paper. And it just ensures that I don't make any mistakes. So I'll see you over in the next video. All right. So first thing I'm going to do is just import the library that I'm going to need. So we're going to use NumPy, numerical Python. So import NumPy as, and we're just going to call it NP, the standard name for it. And this will allow us to use the modules in NumPy that are involved with linear algebra, since we're going to be solving systems of linear equations, and we're also going to have to calculate ranks of a matrix. So the first thing I'm going to do is I'm just going to create a dictionary. Variables, the units of the variables. So P will be density. That's going to be a list. And then we have mu, which is the viscosity. I'll put the list later. I'm just putting all the variables first. We also have velocity of the fluid. And then we have diffusivity. We have the mass transfer coefficient. And then we also have the diameter of the tube. And so this is just a list of key value pairs for density. It's going to give us a list where the first element of the list is just kilograms, what coefficient it is in the units. So for this it's kilograms. Second unit, second position of the list is just meters. So it's kilograms per meter cubed, and then there's no seconds. Viscosity is just kilograms per meter per second. Velocity is just meters per second. Diffusivity is just meters squared per second. Mass transfer coefficient is meters per second, and diameter of the tube is just meters. So this is just, I'm just taking all the variables and giving their associated units. I'm keeping it in a dictionary so I can access it later. Let's see. Alright, so that's all good. And so we want to create our dimensional matrix. So if we look at var units, if we just use the method values, we'll see we just get a list of the unit vectors, the vector of units for each of our variables, like this. And we can stack these lists as columns to get our dimensional matrix. So linear algebra, that's the module in NumPy that allows us to do linear algebra operations, and we want to do rank, matrix rank of this. But we see it takes in values, it takes in lists and tuples, but this is a dictionary values, so we're just going to change the data type to list, like that. And we're just going to use D, big D, and it's the dimensional matrix. And let's just make sure it all goes right. Display D. Let's see what. Three. So that's the rank of our matrix. I kind of skipped a step. I first wanted to make the dimensional matrix. So we column stack like that. Let's see. So 1, -3, 0, 1, -1, and yes. So if you go back to the first part, you'll see this is the matrix that we had, our dimensional matrix. And so now we want to calculate the rank of this. So we'll say little r to represent the rank of the matrix. Use what we did before, the rank, matrix rank of B. And then the number of variables we have is just the length of our dictionary, 6. And so number of dimensionless variables I is just equal to n minus r. we'll see 3. That's the number of dimensionless groups that we have. So just a reminder, we then chose our core variables as we used density, diffusivity, and then we also used the diameter of the tube. And so first thing I'm going to do is make that core matrix that I was talking about, which shows up in all our linear systems of equations when calculating the exponents. So it's a little tricky to be able to make the matrix. So I'm going to first define a list of the variables that we want. So the density, just know when I use dictionary up here and I put P, Python actually converts that to a string, so I have to make sure this is a string, otherwise it's going to say that variable is not defined. So same thing for DAB, and then D. And now what I want to do is go through this list and get the values for these keys. So for I in core, var units, we can use the get method where you put in the key and then it will return the value associated with the key. So get that. I'm going to store these values in a list. So a dot append, like that. I'm going to define what a is first, just like that. And let's see if this works. If we just display a. So first, it's a list of lists. The first list is the units for density, meters per cubic meter. And then second one is the units for diffusivity, meters squared per second. And then the third list is the units for the diameter, which is just meters. And so we can create a core matrix by using a column stack in NumPy. So I'll just call this core matrix column stack A. And we'll display it, just make sure everything goes as planned. So yeah, this is the core matrix we have. So this is A, and then so it's AX equals B. X is what we're solving for. So now we just need to create a list of our B vectors, which we can do using the same thing. So we'll call these the non-core is just K sub C. We also had velocity as a non-core variable, and then we also had viscosity as a non-core variable. And we'll create an empty list to store all the values that we obtained from our dictionary. So for I and non-core, B dot. So we're just going to add to the list units using the get method still. We're going to use I display, make sure we're doing it right. So these are the units for K sub C, meters per second, velocity, meters per second, and viscosity, kilograms per meter per second, which is awesome. That's what we wanted. But remember that on the right-hand side, it's actually negative of the values for the non-core variables. So we're going to just make this, we want to multiply each of these vectors by -1. So first we have to make it an NumPy array. And then we can say b equals -1 times b. Let's make sure then that that worked out correctly. So yeah, 0, -1, 1, which is opposite of what we had before for k sub c, which is 0, 1, -1. And then same thing for velocity, and then same thing we got here for viscosity. So this is our right-hand side of the equation. So now all we have to do is use the linear algebra submodule and solve these systems of equations. So we can do access the linear algebra module in the NumPy library, and then we put solve, and we need our left-hand side, it's the matrix, and then the right-hand side is just the b. In this case, we want the first one, and we'll see what this returns. So this gives us our coefficients for our exponents for our first dimensionless variable. So 3, 1, and 3. Is that right? B density cubed. That's not right. What did we do wrong here? Let's go back a step. Let's display A and display B. Oh, well, I was supposed to use core matrix, not A. My bad. Okay, so we'll just go back and do it again. NumPy.algebra solve. We want the core matrix, and then B0, like that. And see what that returns us. And that's going to give us our exponents for our first dimensionless variable. So it would be density to the 0th power, diffusivity to the -1st power, and then d to the 1st power. And then we have our non-core variable, which would be the mass transfer coefficient. I'm going to be displaying our dimensionless variables using SymPy, and I don't want to deal with floats here, so I can just round these. So I'll say A, I'll get the variables out of this, is equal to round I for I in this. So I have, let's just be that. A, B, C. Okay, I'm going to call these A1, B1, and C1. And I'm just going to do the same thing to get the exponents for this second dimensionless variable. So A2, B2, C2 equals, just copy and paste this. Like that. Except this is now going to be 1, A3, B3 equals, copy and paste it. We want the third element in the B. Do all of that. So let's display, see what our exponents are for the second one, second dimensionless variable. So we'll just display all these. 0, -1, and 1. So that would be d over the diameter over the diffusivity multiplied by our non-core variable, which is velocity. And then we can see what our exponents are for our third dimensionless variable. -1, -1. So that's our non-core variable viscosity over diffusivity over d. So now that I have all this stored, I'm just going to, instead of going back to paper, I'll just use SymPy to display our dimensionless variables as SP. And from SymPy import, that just allows us to access all the modules. So let's just call, we have to make our variables symbols so that Python knows not to freak out since they're not defined variables. So density, viscosity, velocity, diffusivity, mass transfer coefficient, d. We can just symbols, lowercase, and then we do a string, and the separator is just white space. So when you put a space, it knows that that's the next symbol. So we'll use, this is also awesome because we can use Greek letters. So density will show as rho, viscosity, that's mu. Let's just keep velocity as v, EAB, that makes it a subscript when you use underscore, k sub c, and then d. And so first dimensionless variable, that's pi1. That's going to be density raised to a1 multiplied by dAB raised to b1, and then d raised to c1, and then multiplied by our non-core variable, which it was k sub c. Just like that, we can display pi1. So there we go. That's our first dimensionless variable. Second dimensionless variable. Pi2 is what we called it. We'll just copy and paste what we wrote before, just changing the exponents in the non-core variable. So all of these are 2. And our non-core variable for the second dimensionless variable was velocity. And then we'll just display that. And then we'll do the same thing with our third dimensionless variable. My typing skills is not the strongest. Okay. Paste again. These are just 3s now. And our non-core variable was viscosity, so U. And then we just want to display that pi3. And here we go. So we get diameter multiplied by the mass transfer coefficient over the diffusivity for the gas and the liquid. That is our first dimensionless variable. We notice that that is the Sherwood number. Third dimensionless variable we see is, the second dimensionless variable is diameter multiplied by velocity over the diffusivity, and that is just the Schmidt number. And our third dimensionless variable, we were hoping it would be the Reynolds number because that's the dimensionless variable that Sherwood and Gilligand used, but it's not. We have the viscosity over the density over the diffusivity. which is just the kinematic viscosity over the diffusivity. That is the Peclet number, I think. No, okay, sorry. This third one is the Schmidt number, and the second one with the velocity dV over dAB is the Peclet number. Yeah, we had Schmidt equals velocity times d over dAB. D over dAB. The second one is the Schmidt number, and the third one is the Peclet number. So we can just display this. We'll just introduce Sherwood, sp.symbol, Sherwood, and display. We'll use an equation, just equating it. Sherwood is equal to pi 1. We don't need to display that anymore. This one here we said was the Schmidt number. So Schmidt sp.symbol and equation that's equal to pi 2. And then this third one is the Peclet number. We don't want to use that. Well, we could use that, but what they used was the Reynolds number. But when you have these dimensionless variables, you can divide them and get another dimensionless variable. And when we divide pi 2 by pi 3, we get the Reynolds number. So Reynolds, we'll make a symbol for it. Reynolds, and display Reynolds number is just equal to 3 over, like that. It's actually the other way, just like that. And there we go. So we have the Sherwood number, the Schmidt number, and the Reynolds number. And that's the dimensionless variables that we need to describe our situation at hand. And so we are just mimicking this experiment. So we did the first step. We took all the parameters and then we reduced the parameter space by doing dimensional analysis. We have our non-dimensional variables, but now at this point we'd like to run our experiments. So we can do, first we need to come up with our Reynolds and Schmidt numbers. So we can say Reynolds number is just, we can use the random module and uniform. So it's just going to pick random values between, what was our range for the Reynolds number, 2,000 to 35,000. And we want 100 points. We're going to run this experiment 100 times, we're going to say. And Schmidt number, we're going to use the same thing. Random dot uniform, and that went from 0.6 to 2.5. And we want 100 points. So if we just display these, we see we just get a list of 100 points where they're just random values between the lower and upper limits that we set. So if we were running this experiment, it would be these would be the Reynolds and Schmidt numbers that we used, and then we would measure the Sherwood number. But since we're not actually going to be performing the experiment, we're going to use the relationship that Sherwood and Gilligand came up with to get a list of Sherwood numbers And then we are going to introduce some experimental error by using a normal distribution. So we'll just calculate the Sherwood number using the model that Gilligand and Sherwood came up with. So it was 0.023 multiplied by Reynolds number 2, it was 0.83 multiplied by Schmidt number, it was to the 0.44. And we can see what the Sherwood numbers look like. So for the list of Reynolds and Schmidt numbers that we had before is 100, so we ran this experiment 100 times. These would be the Sherwood numbers. If you think about what the experimental data that Sherwood and Gilligand came up with, it's not going to be exactly these values, because these are the values that perfectly fit their relationship, their model that they came up with. But that doesn't describe all their data points. It's just the best model that minimizes the difference between experimental data and what the model predicts. So using these, we can introduce experimental error to get a list of 100 Sherwood numbers that would be similar to what Sherwood and Gilligand would have came up with. So we can use numpy dot, we want to use random again, but we want to use a normal distribution. What that does is that we have a mean and then we have a standard deviation, and it just makes it, the probability that numpy will select a point closer to the mean is higher than picking a number further away from the mean based off whatever the standard deviation is. So we can say our mean value would be Sherwood, and then we want to introduce 10% experimental error, so we can put the standard deviation as 10 times the Sherwood, 10% of the Sherwood number. And that would be the Sherwood numbers that we would get experimentally. So if we display that, just like that. So these are the Sherwood numbers that we would get experimentally. And next thing we're going to be doing is plotting our experimental error, our experimental data, and then we want to then model it and find this surface that best describes our data. So here's all our experimental data, and first thing we're going to do is we're just going to plot it, and we're going to use Plotly. So Python has a package named Plotly, which we can use to make awesome graphs. And first thing we want to do is be able to make a subplot. So we want to do from Plotly the subplot modules, import make a subplot, since we're going to want to make our own subplot. And then on this subplot we're going to want to add a 3D scatter plot. So that's located in Plotly's module graph objects. So we're going to add a graph object to our subplot. And we're going to make a 3D scatter plot, just like that. And the default template for the graphs in Plotly I don't particularly like. I like the dark graphs, so I can just change the default templates. So I could import Plotly Pio, and with that I can change the default template to Plotly dark, just like that. Alright, so now we're just going to create our figure first. So make a subplot. We won't put any values in it, it's just going to make it, the default will be 1. So if we just look at our figure, we just have one plot on our figure, but we want to add our experimental data to it. So we're going to add a trace and we want to use graph object, we want to use the scatter 3D, just like that. And so our X values are going to be our Reynolds numbers that we used. Our Y values are going to be our Schmidt numbers. And our Z values are going to be the Sherwood numbers. And we'll see what that looks like. Alright, so we see we get this nice 3D scatter plot, but we have these lines. We don't want to use those lines, so we got to change the mode that we're using. We're going to change the mode to markers. And that's just going to get rid of the lines and just leave them as it's just going to be points on our graph instead. So if we look at this now we just have points. You see how some of these points are kind of cluttered together. So we're going to shrink the size of our markers, and we're also going to change the color of our markers based off what the Sherwood number is. So when the Sherwood numbers are lower, it will be one color, and then it's like a gradient of colors as the Sherwood number goes up. So we can do that by marker equals dictionary of the properties of the markers. So we can say size, we'll just set that to 3, and then color equals Sherwood. Let's see what that is. And that looks much better. Now we can see every single point without it being cluttered together. And it's much more visually appealing seeing that there's a color gradient based off the magnitude of the Sherwood number. We see we have Z, Y, and X axis. We want to give those names. And we might even want to give this plot a title, and we can change like the height and width of it. So we can do that by using update layout. So we can say height is equal, so this is in pixels. We'll use 900. Width, we can just say 800. We're doing this because we see a lot of blank space in our figure. We don't want that. We want to make it look more professional. We're going to give this a title, and we're going to also name the axes. So we can choose our own font instead of the default font. So I like use font family equals to, that's the font that I like, New Courier. And now we can also give this a title. So we use a dictionary for this, for all the attributes of all the properties of the title. So dictionary, the text was just going to be what it displays. So text is we're going to call this evaporative mass transfer for wetted column. We can change the size of it. We can use size equals 20. And then we can see what this looks like. Let's see. Did I not close that off? What is going on? I think it's font size. There we go. Alright. We see that our title is to the left. We can center it by doing where we want to start it at, so 0.5 halfway, and then we can set an X anchor equal to center, like that. I also don't like how tall this is, so let's bring it down to 600. Let's see what it looks like. Missing a decimal place, a comma. There we go, that looks much nicer. Now we just want to name our axes, so we can also put into the update layout, we can do scene. And this is also just a dictionary. We can do where we use x-axis title. Go to Reynolds. And then z-axis title equal to Sherwood. Now let's see what it looks like. Alright, so there we go. We got a nice little plot here. And next what we're going to want to do is find a relationship between the Sherwood number. We want to find a function. Define Sherwood as a function of the Reynolds number and the Schmidt number. So we're going to find a model that best fits our data. And I'm going to talk about that on paper. So I'll see you in the next video. Alright, so now after Sherwood and Gilligand, they ran their experiments, collected the data, graphed it. They decided that a model that could best fit their data, it kind of looks like a surface like this, where it'd be A times Reynolds to the B times Schmidt to the C. There's also some theoretical reasons for why they chose this model, but we won't get into that. So they decide to choose a model of this form, and their goal is to try to find what A, B, and C are. And so how we're going to do that is first we're going to linearize it, because it'll be easier to deal with. Linear systems of equations are much easier than nonlinear. If we linearize this, we'll see that we get this. We get log of A plus B times the log of the Reynolds number plus C times log of the Schmidt number. That's equal to log of Sherwood. So to linearize this, all you have to do is take the log on both sides and then expand out and bring the exponents down in front of the log signs. And now with this, what we do here is we would plug in our experimental data. In this case, we ran the experiment 100 times. We have 100 data points. And if we did that, we would get something that looks like this. Log of A plus B log of our first Reynolds number plus C times the log of our first Schmidt number plus equals log of our Sherwood number. And I'm not looking at notes right now, just so you know. I am making sure my paper is in frame. And we do that for all of our data points. Just show these go down until we get log of A still, B log of our kth Reynolds number, plus C log of our kth Schmidt number equals log of our kth Sherwood number, like this. And so it's this system that we're trying to solve. And if we put this in matrix vector form, it's going to look like this. The first column is just going to be all ones. ones like that. Second column is just the log of our experimental Reynolds numbers. So the first Reynolds number all the way up to the log of our kth Reynolds number, which is just the number of experiments we had. In this case it was 100. And then we have the log of our Schmidt numbers in the third column, all the way to our kth log of our kth Schmidt number. That's our matrix. Multiplied is the log of A, B, and C. What's that equal to? That's equal to the vector log of our Sherwood numbers. So this is the system we're trying to solve. We're seeing what is log of A, what is B, what is C. And could you come up with A, B, and C such that when you put them into all of these equations, you get the exact answer over here, your experimental data? In other words, can you find A, B, and C such that your model perfectly fits your data? And that's ridiculous because there's experimental error. You want to try to find the best model that fits it. There is no A, B, and C that satisfies this. If we were to just write this differently, we're going back to linear algebra, AX equals B, like this. So A is this matrix here, X is log of A, B, and C, what we're trying to solve for, and B is the log of our Sherwood numbers, just like that. If we're trying to solve this linear system of equations like this, there's a solution that exists only when this vector B is in the column space of A. We know that there is no solution that exists because if there was an A, B, and C that perfectly fitted our data, then either we just did the experiment like without any error, and it's highly unlikely. So B, we know, isn't really in the column space of this matrix, and by column space I mean like linear combinations of this this column and this column and this column. We can think of this geometrically as we just draw some surface here in like kind of 3D space. This is the column space of our matrix A. If B was in the column space, then there would be an A, B, and C that perfectly satisfies our data. But there isn't. B, which is the log of our Sherwood numbers, is actually outside the column space of our matrix. And so if we were to go here and try to find A, B, and C that satisfies this, there is no A, B, and C. There is no solution that exists. So you could either give up, or you can find, well, what A, B, and C gives me the closest solution. So what A, B, and C can I plug in here that gives me a vector that is the closest to this B vector? And the closest you can possibly get to this B vector right here is just the projection of this vector onto our column space. So we can draw that like this. That vector right there is this vector projected onto our column space. And then there's also this vector here, which we'll call B perpendicular. It's the perpendicular vector of B. It's perpendicular to our column space. And this vector right here we'll call B parallel. This is the closest we can possibly get to this vector. So this we can't solve. But what we can solve is AX is equal to B parallel, like this. The closest solution to this equation right here is the exact solution to AX equals B parallel, the projection of B onto the column space, which it's just a linear combination of the B vector and the perpendicular vector. So if we were B parallel is just B vector, which was up here, minus the perpendicular vector. This B perpendicular is orthogonal to our column space. And if we multiply A transpose on both sides, we're going to see something cool. Equals A transpose B minus A transpose B perpendicular. And A transpose multiplied by B perpendicular is just 0. I can show that pretty easily by if we just write A, if it's just A, this vector is the first column all the way up to the kth column like this. If we look at A transpose, it's then all these columns become rows. So the first row is A1 transpose the way up. Then we get AK transpose like that. And then if we look at A transpose multiplied by B perpendicular, we're going to get, let's just write it out. A1 transpose, so I'm just writing down what A transpose here is. K multiplied by perpendicular, and this then is just equal to one-dimensional array, and it's the inner product of A1 transpose with B perp, like this, inner product, dot product, whatever, and AK transpose B perp. And this is what's cool, is that this, what the inner product is equal to, is just the magnitude of this vector times the magnitude of this multiplied by the cosine of the angle between them. But B perp is orthogonal to everything in our column space. So the angle is 90 degrees, cosine of 90 degrees is 0, so all of this is just equal to 0 vector. So it cancels out from our equation up here. And so then we're left with A transpose A x equals A transpose B. And then if we just take the inverse of this on both sides, we'll get the identity matrix over here and isolate x by itself. And so then we get x equals A transpose A, inverse of that matrix, multiplied by A transpose multiplied by B. This right here, in our case, x will represent log of A, B, and C. And then that's how we can find what A, B, and C are for this. We can't actually solve the exact solution. We can't find a model that goes through all of our points, but we can find the best possible A, B, and C that best fits our data. So we're going to be using this, and this A transpose A here is called the Moore-Penrose inverse. And it's a nice method because up here you see a B parallel, you also have B perp. You could just get rid of this right here and solve this, but that would require you to then project your B vector onto your column space, which requires more work. You expand it out like this, and B perp, this A transpose gets rid of it, and you can solve it without ever actually having to calculate B perp or B parallel, which is really nice. Alright, I'll see you in the next video. Alright, so now that we talked about how we're going to actually solve for A, B, and C to fit our model using the Penrose, Moore-Penrose pseudo-inverse, we're just going to use NumPy, the linear algebra module in it, to do all of those linear algebra operations for us. So the first thing we got to do is create our matrix A that we just talked about. So first thing, we're going to just make a matrix based off of columns. So we use column stack, and the first column we saw was just ones, so we can use ones like, which it's going to give us a list of all ones, and the length of that list is going to be whatever you insert here. It's going to be like, so we'll use Reynolds here. Since the Reynolds has 100 values, this is going to give us a list of 100 ones, just like that. We saw our second column is just the log of our Reynolds numbers, and our third column was just the log of the Schmidt numbers. And we use column stacks, so you have to use one argument, so you actually input this whole thing as a list, just like that. See what A looks like. There it is. Just first column is all ones, second column is the log of our Reynolds numbers, and the third column is the log of our Schmidt numbers. And then we just need our B vector that was on the right hand side, which was just the log of the Schmidt numbers. So we can say B is equal to the log of our Sherwood numbers, just like that. You can even see what B looks like. The length of this is just 100, and it's the log of all our Sherwood numbers. And now we're going to use that formula that we just came up with to calculate what A, B, and C are. So we're going to be using matrix operations, and so we saw that it was the inverse of A transpose multiplied by the A matrix. So we can do A dot T like that. That's transpose of matrix A. And then when you do matrix multiplication, you use the at symbol. So at A. But we want the inverse of whatever that matrix is. So we do go to the linear algebra module in NumPy, and we do inverse like that. And then we multiplied that, our transpose matrix, which was then multiplied by the log of our Sherwood numbers. And we'll see what this is. And there we go. We see this first thing is the log of A, and the second one is our B value, and the third one's our C value. So we can say I don't want to call this first value A, since it's really the log of A, so I'll just use log of A1, and then we'll say B1 and C1 is equal to this. And then we can say A1 is just equal to, we want to get what actually A1 is, so we just use the inverse of the log, which is exponential. So exponential to we want log of A1, just like that. And now we can display what A1, B1, and C1 are. And we get 0.022, 0.83, and 0.42, which are very close to what Sherwood and Gilligand came up with. We saw up here 0.023, we have 0.022, and then they had 0.83 and 0.44, and we got 0.83 right on the dot, and then 0.42. So we're pretty close to what they were able to get. We can also solve for this using defining a sum square error function and then minimizing it. So I'll first define what a sum square error is. It's going to take in some argument p, and it's going to return the difference between our experimental data minus what our model would predict. So it would be, we're going to keep it linearized too, so it's going to be np.log, so it's the log of the Sherwood number. That's what our experimental data is, and we want to see what the difference between that is and what our model would predict. So our model would is just log of, I'll call this A2, so NP, I guess I don't want to call it log, I'm going to keep it as just a number, so log of A2 plus B2 multiplied by the log of our Reynolds number plus C2 multiplied by the log of our Schmidt number. So this in parentheses right here is what our model would predict. And we're going to try to figure out what this log A2 variable is, this B2, and the C2 is. But since the difference between our experimental data and our model could be positive or negative, we just want to square this so we're only dealing with positive numbers. Otherwise, deviations would cancel out based off if they're positive or negative, and we don't want that. So we're going to square this whole thing. Square, just like that. And we want to calculate this difference over our entire data set. So we're going to want to sum. So we can use this sum function in the NumPy library, just like that. And we want our function to return this. However, I defined new variables here, the log A2, B2, and C2. That's just what we input into this function right here, P. So I have to define explicitly what those are. So I can say log A2, B2, C2. That's just whatever's inputted into this function, like that. Return, let's see, no errors, that's good. And now we want to minimize this function. And Python has a package called SciPy, and SciPy has a module called optimize. And inside that module, there's a function called minimize. And that's the function we're going to use. So we're going to have to import that. So from SciPy.optimize, we want to import the minimize function, like that. And now we can use the minimize function. So we say minimize, let's see what it needs. It needs the function we're trying to minimize, which is the sum square error that we just defined. And then it needs an initial guess. So our initial guess for A, just remember that it's not what A actually is, it's the log of A. We'll just say it's -3, and then based off what Sherwood and Gilligand came up with, we'll just use those as like approximations. So we'll say 0.8 for B, and then we can say for C we can use 0.4. And let's see if it returns anything. So optimization terminated successfully. The Sherwood. Yep, that's wrong. It's squaring what our model predicts, not the entire difference. So I need another parentheses in there. That's why I was looking so weird. Now let's see what we get. What's going on here? want to square here. It was just squaring our log of our Schmidt number. Now I'm confident it will work. There we go. Alright. So here it returns a class object and has an attribute called x right here, and this is our solution. And we want to access that, so we can just use .x like that, and then we can call we can access then what A2, B2, and C2 are. C2 equals that. We want to see what A2 is, so we'll say A2. We just have to exponentiate the log of A2. So this, and now we can display A2, B2, and C2. And there we go. We get 0.22139, which is very close to what we got before. 0.8342, 0.4. We get pretty much exactly what we got before, which makes sense because you're using least squares here to find the model of best fit. And these are just two different ways to basically say the same thing. Alright, so now that we have what our model is, we are going to want to graph that over our experimental data. So the first thing we're going to need is, well, which exponents are we going to use? I'm just going to use A1, B1, and C1. But I'm just going to redefine them as A, B, and C, so I don't have to keep track of, I don't want to say A1, B1, and C1. A1, B1, C1. Just make sure we don't get propagation of an error here. Alright, awesome. What did I just, no. There, let's make sure. Okay, good. So we're going to want to graph our Reynolds number over our entire range. So we're going to use, we can say Reynolds is just equal to linear lin space. So we want it to range from, what was it, 2,000, 2e to the 3 to 35,000. And how many points do we want to use? We can just use 20 points like that. And then we can do the same thing with our Schmidt numbers. mp.linspace. The range of that was 0.6 to 2.5. And we want 20 of those. So this is just giving, for the Schmidt number, it's from 0.6 to 2.5. And it's giving us 20 points between those two numbers, linearly spaced. So we can even just display what Reynolds is and what Schmidt is. There we go. So the Reynolds is just from 2,000 to 35,000, 20 points where they're all spaced equally apart. And then the Schmidt numbers are just from 0.6 to 2.5, there's 20 points, and spacing between each point is equal. And now what we're going to be doing here is we want to make a wireframe plot. And what a wireframe plot is you're taking a set of points from your independent variables and you're projecting it up onto the surface of your plot. And it makes for a great representation of data, and it's called wireframe because it's going to look like a bunch of wires just together. So we'll see that. But in order to do that, we have to use something called a mesh grid. Because in order to make this, what we're going to do is first we're going to take the Reynolds number. We're going to set the Schmidt number to be a constant, like 0.6. And then we're going to vary the Reynolds number and then graph that line. And then we're going to go to the next Schmidt number and then vary the Reynolds number and plot that line. And once we go through all of those, keeping the Schmidt numbers constant, what we're going to have is a bunch of lines parallel to the x-axis, the Reynolds number axis. And then after that, we're going to want to do the exact same thing, but in reverse. We're going to want to hold Reynolds constant and vary the Schmidt number, and that's going to give us lines that are parallel to the other axis. So we use a mesh grid here, and so you can see exactly what a mesh grid is. I'm just going to create two lists. List 1, let's call it 1, 2, 3, 4, 5. And then list 2, call it 6, 7, 8, 9, and 10. And we can call this, we're going to use mesh grid, which is in the NumPy library. Mesh grid of list 1 and list 2. And just see what this gives us. We don't need that anymore. So there it is. What it gives us is two different arrays, where the first array is just giving, it's taking list 1 and varying it through its entire range. And then the second array is the second list, but it's holding it constant. So how we're going to be graphing this, if we were to graph this, we would graph the first element of this first array with the first element of this second array. So as 6 is held constant, we would vary from 1, 2, 3, 4, and 5. And after that's completed, then we can go to the second elements of these two different arrays and plot that. So that would be graphing 1, 2, 3, 4, 5, but as holding 7 constant. And then so on until we go through the entire range of this second list right here. And so that's what we're going to want to be doing with our Reynolds numbers and our Schmidt numbers. So we can just go ahead, we'll call it Reynolds grid and Schmidt grid is equal to np.meshGrid. So the second thing you input is going to be the one that's going to be held constant. So you're going to have lines that are orthogonal to that axis. So Reynolds and Schmidt. So it's going to give us Reynolds grid is just going to be all the Reynolds numbers from 2,000 to 35,000. And then the Schmidt numbers are going to remain constant. We just display, let's look at Reynolds grid. So it's going to be an array where an array of lists, and each list is just the numbers going from 2,000 to 35,000. And then we can also display our Schmidt grid, that, and our Schmidt grid is just holding the Schmidt numbers constant, so 0.6, 0.7, 0.8. And then, so how we're going to graph this is we're going to use this first element here. I guess it's better to talk about it from this angle. So we're going to have the Schmidt number be 0.6, and with the Schmidt number being held constant at 0.6, we're going to graph what our model predicts for all the Reynolds numbers between 2,000 and 35,000, these 20 points. And then after we get done with that, we're going to jump to the next Schmidt number, which is 0.7, and do the same thing until we go through all the different elements. So first now we have to calculate what the Sherwood number is. So Sherwood grid, it's what our model predicts. which was A times Reynolds grid raised to the B. And then we have Schmidt grid raised to the C. We can even display the Sherwood grid. Capitalized, because that's how I defined it. And there we go. So for this first list here is going to be for a Schmidt number of 0.6. It's going off and varying the Reynolds number from 2,000 to 35,000, 20 points, and these are the corresponding Sherwood numbers. And then the second list is the same thing, but we're holding then the Schmidt number constant at 0.7 and varying the Reynolds number. So it's giving us just lines parallel to the Reynolds number axis. So we can actually now just go and plot this using a 3D scatter plot in Plotly, just like we did before. So we can add a trace. Well, actually, no. We have to use something called a zip function. And what the zip function is that it's going to take, if you have two lists with elements in it, the zip function is just going to pair 1 to 1. So the first element of this list with the first element of this list. So that's what we have to use, that so that we can pair the first element of our Sherwood grid list with the first element of our Reynolds grid and the Schmidt grid. And then for each of those pairs, for groups of those, we're going to graph the line, and then it's going to go to the next element, and then graph that line, and then so on. So we can say we can just say an instance of Reynolds and instance of Schmidt and instant of Sherwood in zip. So we're zipping these up just 1 to 1. I'm going to use Reynolds grid, Schmidt grid, and Sherwood grid. So for each one now, we go off and graph it. So we're going to figure dot add trace. We want scatter 3D plot, just like before, where X is going to be our instance of the Reynolds, our Y is going to be the instance of Schmidt, and the Z is going to be equal to the instance of the Sherwood. We also want to change the mode here. It would give us lines, but it's also going to show the markers and everything, and it gets cluttered and everything, so we're just going to change the mode to just show lines. So mode equals lines, and then we can, if we were to plot this right now, all the lines would be different colors and it wouldn't look good, so we just want to keep every single line the same color. So we can say line color equals gray. And let's see if this works. Figure. And there we go. So we're holding the Schmidt constant, Schmidt numbers constant, and then graphing these lines. So there's 20 lines here from 0.6 to 2.5, and for each of those values of the Schmidt, we're varying the Reynolds number. So we get all these lines that are parallel to the Reynolds axis, like this. And now all we want to do is do the same thing, but this time we're going to hold the Reynolds number constant and vary the Schmidt number. And so It's the exact same thing we did before, but it's just going to be, we can literally just copy this, paste it down here, but we have to change which one is being held constant. This time we want Reynolds grid be held constant. Just like that. And this should do the same thing we did before, but this time Reynolds is going to be, the Reynolds number is going to be held constant. And there we go. That's our surface. And that is our what our model predicts. And we see that it fits our experimental data really nice. Just to clean up the figure a little bit more, we can get rid of this legend here. We can just use the update layout method we did before. Update layout, show legend equals false. Yeah, that's all we need to do. And there we go. That is all our data. It's 100 points. And then we have a wireframe plot of what our model predicts. We see that it fits our data very well. We have a nice little graph here. We can even zoom in and out. It's very nice. This is why I like Plotly. There we go. Alright, thank you for watching, and take care.